We've already alluded to attacks on hashes. Now let's learn some more details, including how to defend against these attacks. One crucial application for cryptographic hash functions is for authentication. Think about when you log into your email account. You enter your email address and password. What do you think happens in the background for the email system to authenticate you? It has to verify that the password you entered is the correct one for your account. You could just take the user-supplied password and look up the password on file for the given account and compare them, right? If they're the same, then the user is authenticated. Seems like a simple solution, but does that seem secure to you? In the authentication scenario, we'd have to store user passwords in plain text somewhere. That's a terrible idea. You should never, ever store sensitive information like passwords in plain text. Instead, you should do what pretty much every authentication system does. Store a hash of the password instead of the password itself. When you log into your email account, the password you entered is run through the hashing function, and then the resulting hash digest is compared against the hash on file. If the hashes match, then we know the password is correct and you're authenticated. Passwords shouldn't be stored in plain text, because if your systems are compromised, passwords for other accounts are ultimate prize for the attacker. If an attacker manages to gain access to your system and can just copy the database of accounts and passwords, this would obviously be a bad situation. By only storing password hashes, the worst the attacker would be able to recover would be password hashes, which aren't really useful on their own. What if the attacker wanted to figure out what passwords correspond to the hashes they stole? They would perform a brute force attack against the password hash database. This is where the attacker just tries all possible input values until a resulting hash matches the one they're trying to recover the plaintext for. Once there's a match, we know that the input that's generated that matches the hash is the corresponding password. As you can imagine, a brute force attack can be very computationally intensive, depending on the hashing function used. An important characteristic to call out about brute force attacks is technically they're impossible to protect against completely. A successful brute force attack against even the most secure system imaginable is a function of attacker time and resources. If an attacker has unlimited time and/or resources, any system can be brute forced. Yikes. So, the best we can do to protect against these attacks is to raise the bar. Make it sufficiently time and resource intensive so that it's not practically feasible in a useful time frame or with existing technology. Another common method to help raise the computational bar and protect against brute force attacks is to run the password through the hashing function multiple times, sometimes through thousands of iterations. This would require significantly more computations for each password guess attempt. That brings us to the topic of rainbow tables. Don't be fooled by the colorful name. These tables are used by bad actors to help speed up the process of recovering passwords from stolen password hashes. A rainbow table is just a pre-computed table of all possible password values and their corresponding hashes. The idea behind rainbow table attacks is to trade computational power for disk space. By pre-computing the hashes and storing them in a table, an attacker can determine what the corresponding password is for a given hash by just looking up the hash in their rainbow table. This is unlike a brute force attack, where the hash is computed for each guess attempt. It's possible to download rainbow tables from the internet for popular password lists and hashing functions. This further reduces the need for computational resources, requiring large amounts of storage space to keep all the password and hash data. So you may be wondering how you can protect against these pre-computed rainbow tables. That's where salts come into play. And no, I'm not talking about table salt. A password salt is additional randomized data that's added into the hashing function to generate a hash that's unique to the password and salt combination. Here's how it works. A randomly chosen large salt is concatenated, or tacked onto the end of, the password. The combination of salt and password is then run through the hashing function to generate the hash, which is then stored alongside the salt. What this means now, for an attacker, is that they'd have to compute a rainbow table for each possible salt value. If a large salt is used, the computational and storage requirements to generate useful rainbow tables becomes almost infeasible. Early Unix systems used a 12-bit salt, which amounts to a total of 4,096 possible salts. So an attacker would have to generate hashes for every password in their database, 4,096 times over. Modern systems like Linux, BSD, and Solaris use a 128-bit salt. That means there are 2 to the 128th power possible salt values, which is over 340 undecillion. That's 340 with 36 zeros following. Clearly, 128-bit salt raises the bar high enough that a rainbow table attack wouldn't be possible in any realistic time frame. Just another scenario when adding salt to something makes it even better. That rounds out our lesson on hashing functions. Up next, we'll talk about real-world applications of cryptography and explain how it's used in various applications and protocols. But first, a project that will help you get hands-on with hashing. #GetItDone.